Welcome everyone to my course Formal Methods for System Verification. In today we will start formal property verification. So far in the class we have learned mostly on the SAT based verification, right. So, here we basically try to model my verification problem as a property and then I use any satisfiability solver or SAT solver to check whether the property is satisfiable or unsatisfiable, right. And based on your modeling we check whether the satisfiability means maybe it is correct or maybe unsatisfiable, maybe it is correct, right. The way you have modeled, it depends on that. The other way of verification is the formal property verification, right. So, in formal property verification what happens? So, you basically have a design and you have set of properties, right, and you want to check whether your design is satisfying those properties or not, right. So, overall process, let me try to clarify. So, everything start with some design specification, right. So, the specification can be in English language document where you basically talks about what are the things you want to get, you want to implement in the implementation, and you may have also some timing diagram, some block diagram, some figure, some flow chart, something, right. So, in a specification you can have everything. So, from there the design engineer, right, who will see this and he understand, oh, I have to achieve this. So, this will be my Verilog code, right. So, seeing the specification, the design engineer will get the implementation. Your implementation may be in Verilog, VHDL or system Verilog, right. And the verification engineer who will also take the same specification, okay. So, he will read it, he will understand it and will identify the set of properties which has to be checked on this implementation, right. So, he understand what are the correctness properties. So, if somebody implement this, what are the property or the correctness things this implementation has to satisfy, he will identify, and these are two independent tasks, right. So, design engineer and verification usually do it independently. You see that there can be 100 different implementation of the same thing, right. You may use different logics, say somebody may use let us say you want to implement something in some sorting algorithm, say, right, and then somebody can use merge sort, somebody may use quick sort, somebody may use selection sort. You can implement everything in Verilog, right. Somebody may create a pipeline architecture, somebody may create a fully unrolled architecture, somebody use only register, somebody use memories, right. Somebody try to reduce the delay of the circuit, somebody try to reduce the power of the circuit, somebody try to reduce the area of the design, right. So, all these things can happen and you can, for every aspect you may get a different design. So, for a single specification you can have 100 different implementations, right, but the correctness property is unique, right. Whatever the implementation, if it is sorting algorithm, it does not matter whether you optimize for area, power or delay, at the end of the day it should sort your inputs, right. So, this correctness property will basically encode those things, right. So, this is independent task, and then you have this formal property verification which basically check whether this implementation satisfy these properties or not, right. So, if your implementation satisfy those properties, that means your implementation is correct, okay. So, this is the overall formal property verification approach, right. So, now if you see here, what are the main tasks here? The main task is that for the verification engineer, he has to identify the properties. So, he reads the document, all the timing diagram, and he identify these are the things should satisfy, okay. And then he has to also ensure that he has done his job correctly, right. It means he has write the correct set of properties, right. So, it is basically in verification terms correctness, consistency and completeness, right. The property should not be incorrect, right. So, if your property is incorrect, there is no point of doing the verification. He has to make sure that he has rightly identified the correct properties. He identified many properties and they are consistent, it means they are not contradicting each other, and they are complete, in the sense I have written enough properties. If say probably I have written 10 properties, and if I check this 10, it means implementation is correct, there is no 11th property or 12th property. So, this 10 is sufficient, right. So, he has to ensure this correctness, consistency and completeness of the properties that he has written, and most of the time this task is manual, right. So, it is depends on the verification experts, engineer expertise, he just read it and makes sure that he has done these things correctly. Once the property is identified, Then this implementation tool, which is say formal verification, that will check whether implementation satisfy those properties or not. So, you basically have two type of checking. One is called formal way, right. It is basically making sure that your implementation satisfy this property in a mathematical or formal way. So, in this case what we do, we have the set of properties and we have the implementation. So, from the implementation we extract a transition system. Okay. So, you basically have to have a formal model your implementation, right, which in a model checking term or in this formal verification term is called Kripke structure. I will talk about that more in detail in subsequent lectures. And then you have a algorithm, model checkers, right. Basically check whether this transition system satisfy this property or not. If this is M, this is P, it is just check whether M satisfy the property or not. So, this is what this model checker does. Okay. So, in this course what we are mostly focus on, the first of all somebody has to write the properties. So, what are the, how do write the properties, right, what logic, is it proposition logic or something else. So, usually the properties are written in temporal logic. Okay. Here why it is temporal logic, you have time is involved here, right. In a sequential system you think about not your you are getting your output in one clock, right. For a combinational circuit it is just one clock, there is no time, right, instant you will get the output. But in a sequential circuit you think about that I give so suppose I am doing a sorting algorithm, the example I am taking, maybe it is taking 20 cycle. So, only after 20 cycle you will get your output. Okay. So, there are time involved here. So, in this temporal logic you have all the proposition logic that we have discussed for our SAT solving, all this proposition logic context are there, and you have also some operator which is called temporal operator, right. So, this temporal operator will captures your time. Just to give you some example, let us say I am saying that if you request, so suppose there is a resource. So, if somebody request it, within 2 cycle he should get the resource, right. So, now you are saying within 2 cycle, how do you model this? Or you are saying there is no starvation, in the sense say if somebody request, eventually he should get the access of the resource, right. It may not be 2 cycle, it may be 2 cycle, 3 cycle, 10 cycle, 20 cycle, but he has to get that. So, that he is not starving, right. So, when you write this kind of properties, that something is requested within 3 cycle, within eventually in a finite time it should get that and all, right. So, this there you need time, the timing operator, and those temporal operators are there. So, I will introduce them today. So, this is what this formal property verification, where you need to know this temporal logic, how do you encode the property, right. So, this is one thing, and in this course we will learn that. So, given a specification, how do you encode, you identify the properties and how do you encode them in temporal logic. Okay. So, that is the first part. The second part is basically the model checkers, how this magic happens, right. You have the properties which is some temporal logic, you have a FSM which is basically a Kripke structure, and this property will be checked in this Kripke structure, and that is what this model checker does, right. So, how it is happening, what is the algorithm behind, which we need to understand that, right. So, even if you are a verification engineer, you are writing the property, you should know how it is going to check, right. Sometime checking a property may be difficult, some property may be checking easier. So, all those things we will discuss in subsequent classes. So, you must aware that what is happening in background, right. And similarly, this transition system is too big, your probably it will take 2 time, right. So, the way you are modeling, how do you break your circuit into small part, so many factors are there. So, you must know what is happening there, right. So, in this course we will also cover that, the algorithm behind this model checkers. Okay. So, this is also called static assertion based verification. Assertion is basically property or formal verification, right. So, this is basically formal property verification. Okay. So, the other one is called dynamic assertion based verification. It is just like your simulation, right. So, in simulation what we do, we basically create test cases and you run the implementation, right. So, when you basically write a C program, let us say, and you what you do in your assignment, you just create some test case and run and see whether your output is correct. So, that means you know what is your golden output, right, what is the correct output and what output your implementation is giving and whether that check equivalent or not, right. So, this is simulation based verification. So, here we are not only checking the final outcome, there may be some problem internally, right. So, this assertions, which is the properties, is written in terms of some signals of the design, right, or your implementation or your program, right. And I will basically take all these signals on which the property is written, and I will also check those internal values, and I will check whether those actually satisfying by the implementation, right. So, the difference between formal property verification is there is no input, we mathematically prove that the implementation is satisfied with the property. Okay. Here what I am doing, I am still writing this property and I embed them inside the code, right. So, I have these properties, and so I will just check the intermediate values of the implementation whether they satisfy these properties or not. So, here I am checking in terms of values, right. So, the example I have given that if there is a request, within 2 cycle you should get the access. So, whenever say some request R1 is true here, I will just check after 2 cycle what was the corresponding grant, right. If that grant is 1, that means this property is satisfied. In some cases it is not true within 2 cycle, I will say, oh, this property is failed. So, here I am not checking mathematically or formally, but based on the input values, right. So, in what is happening here, so you have the implementation, you have the properties, you have the assertion monitor, it basically just the thing I talked about, it just cross check the values that is getting, and you are giving a test case here, right. So, you are giving test case, you are actually simulating your implementation, you get actual values of all intermediate signals, and you are just monitoring these intermediate signals and check whether those intermediate values satisfy the property that I have written, right. And you also have the part where you basically decide what test case will generate. Is it a random test case, or I am doing some guided test case generation, right. So, that I cover most out of my code or the most of my implementation, right. So, that is a different part. But this is, you understand that here we are not mathematically checking, we are just monitoring the intermediate values and making sure that all the property is getting satisfied by intermediate values for the test cases on which I am running my implementation, right. So, this cannot give 100% correctness, as we discussed earlier, only formal methods can give 100% correctness, but this is also a good way of giving a confidence that my implementation is mostly correct, because I run for say 10,000 design which cover 100% of my code, is the branch coverage or line coverage, and I do not find any violation of the property, right. That means the implementation is mostly correct, right. But this gives very good confidence, but may not give the 100% correctness. There may be some very corner combinations on which some property may be violated, which cannot be identified this, because here everything depends on the test case that on which you are running, right. But whatever it is, you need the properties, right. So, even if you are relying on a dynamic assertion based verification, still you need to write the properties and you have to check all those things, right. So, whether you interested in formal verification or dynamic assertion based verification, you need to write properties and you need to not learn this temporal logic. Okay. So, this part of the courses will be useful even if your objective is only the dynamic assertion based verification. Okay. So, as I mentioned, the verification will make sure that he has written the good properties, correct properties, and then you need to verify, right. So, this verification algorithm I will discuss over the future classes. Today I will just introduce the temporal logic, right. What are these temporal logics are there and what is their interpretation. Okay. So, there are 4 temporal operators as I talked about. You have X, which is called next, you have G, which is global, then you have F, which is future, and you have kind of U, which is called until. Okay. So, there are 4 temporal operators. So, I will talk about them. So, here as I mentioned, it is basically temporal or time, right. So, you have to think about a sequence of event, right. You can think about sequence of state transitions, every state is 1 clock, right. You think about a FSM which represent your controller of your implementation. So, in clock 1 I am doing this, then I go to state 2 which is my clock 2, then I am going to state 3 which is my clock 3, and so on, right. So, each state is basically 1 clock or 1 time unit, right. So, if you think about I am in S0, this may be time equal to 1, then I am going to S2, this is clock equal to 2, then S3 which is time equal to 3, and so on, right. So, this is basically, you think about it is a linear, right. There is a path, execution path, and which I am checking something, right. and what I have to check is basically something is happening in future, right. I am somewhere here and I am going to check something is happening in future. The first operator is called next operator, is basically just immediate next state, right. So, for example, say if something, say some p, some property, let us say p holds here or proposition holds here, then I will write S0 satisfy p, right. That means p is true in state S0. Now, if p holds here, also holds here, then I can say S0 also satisfy next p, right. It means p holds in the next state. So that means something S0 satisfy next p if p holds in S1, right. Just immediate next state, something is true, then I will say S0 satisfy next p. If S0 satisfy p if p holds in S0, and S0 satisfy next p if p holds in next state in S1. Okay, it is very clear. Then you have the future operator, which is basically eventually something is true, right. It is not immediately next state, it may be in second state, it may be in the next state, it may be in the same state also, it may be in the next state, it may be after 5 state, it may be in next state, but it has to satisfy within finite time. Okay. So, how do I say this? Say for example, I have a state transition like this S0, S1, S2, S3, S4. So, here say p holds here in S4, then I still write S0 satisfy future of future p, because in after some time, after 4th state it is happening. Even S1 is also satisfying future p, because for S1 also in future p is true somewhere, right. Similarly, S2 also satisfying future p, because for F2 also there is a future. Similarly, S3 also satisfying future p, okay. And even S4 is satisfying future p, because future includes my present state also, that is the convention. Okay. So, it is basically not immediate next state, but somewhere in future which is in finite time. Okay. So, this is future. Then you have global, it means it is true everywhere, right. So, I am taking a path or execution sequence and its p is true everywhere, right. So, p is true in S0, p is true in S1, p is true in S2, p is true in S3, and S4 p is true in S4, and you see here in previous cases I just put a dot dot, that means it infinite sequence. I do not know what is happening after that, but global means the path is infinite. So, here all the trace I will talk about is the infinite trace, and because I am just checking for S0 and a p holds in S4, I do not need to check what happened after that, but for global it has to choke true globally, that means in all the time, in all state. So, even if the path is infinite, it has to hold in all state. So, that is why I put a cycle here, right. So, that means it is an infinite path, right. So, sequence is like S0, S1, S2, S3, S4 and S4, 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 it will repeat like S4 ever, right. So, it is an infinite path, and you see p holds here, 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 and p will keep holding all the state in my path. Then I will say p is globally true, right. So, that means S0 satisfy global p, right. Similarly, S1 also satisfying globally p, S2 also satisfying globally p. So, it means basically from the start, from the state, the current state and all future state in this trace or path p is holding. So, it is globally true. Okay. Next is until. Okay. What is until operator? It is something is holding until something supposed to hold, right. So, if I write p until q, that means p is true until q is true, right. So, you take an example here, I have see S0, S1, S2, S3, S4 and all, q holds here, right, in S3, and p holds in S0, S1 and S2. So, then I can write S0 satisfying p until q. Why? P holds in S0, S1, S2 and q holds. So, here I am saying p is true until q is true, but q has to be true somewhere, right. You cannot have a path where only p true, then p until q does not hold, right. So, you think about, I have taken S0, S1, S2 S3, S4, and then there is a loop here, and say P holds here. So, eventually P always holds, Q never holds, right. Then this S0 does not satisfy P until Q, because Q never holds, P holds, but until Q holds does not hold, right. It is basically P is always true. So, S0 satisfy globally P, but it does not satisfy P until Q, right. So, to some state satisfying P until Q, it means Q has to hold somewhere in future. Okay. But it may be that Q holds in the first state itself, then also I will say S0 satisfying P until Q, right, P until Q, because here Q already holds, right. So, I do not need to check P. So, by virtue is P until Q holds here, right. So, but as I mentioned, in this case S0 does not satisfy P until Q, right. So, until operator is basically relation between two things, something is happening until something else is happening. Okay. So, this 4 operator is enough to model any timing related properties, we will see that. Okay. So, there are two type of temporal logic, one is called linear temporal logic or LTL, the other one is called computational tree logic or CTL. Okay. So, these are just two different way of encoding properties. So, for hardware mostly we use LTL, for other applications we also use CTL. So, LTL is defined over linearly, because it is a linear temporal logic, means it is linearly over path, right. So, this is over path. So, whatever I discuss so far, this is I am defining only one path, right. So, these are all LTL property what I was talking about, and for that this 4 operator that I have talked about, just X, F, G and U is sufficient. For computational tree logic, I am checking all possible path, right. From a state I will check all possible paths. So, all branch. So, that is a branching logic, you have multiple branch. See, for example, like this. So, from S0 you can have this path, that path and so on. So, you can think about there is another state here, another state here, right, and then you have something like this, and it is infinite actually, right. So, you basically think about all possible execution from a state. So, it will create all possible path from this state, right. So, this will give you the tree, right. So, that is why this is computational tree logic, where we basically create all possible computation possible from every state, it will create me a tree, and I am going to check property on that. Okay. So, in this case you need again this 4 temporal operator X, F, G and U, and also you need a path quantifier A and E, because earlier there is a single path, I do not need any path quantifier. Okay. And now I need 2 path quantifier A and E, which is basically A is kind of for all, that means if you are writing A F phi A F P, that means for all path starting from this state in future P is holding, it is basically true for all paths. And E is kind of there exist, it means there exists a path from here on which something holds. So, there may be many paths, but if one of the path holds something, then I will say there exists EFP, say EFP holds, right. So, A implies for all paths and E implies there exists a path, right. So, now if I try to explain this, say for example, here in this case, so in this example let us say I want to check what is happening to this. You see here Q holds here and Q holds here, there are 2 paths here. So, the example I have taken, there are 2 paths. So, this is one path and this is one path, right. So, in all path Q holds in future, right. So, for this path also Q holds in future, in this path also Q holds in future. So, I can write S0 satisfy AFQ, that means in all path in future Q holds, right. So, the interpretation of F remain the same, that in future something holds, whether it is happening for all path or some path is basically given by A or E. Now, you see here I have another example, in this path Q does not hold, right. So, Q never holds, but in this path Q holds here. So, this path satisfy FQ. Now, from this state there are 2 path and one path Q holds. So, I will say S0 satisfy EFQ, there exists a path in which future Q holds, but this S0 does not satisfy AFQ, because there is a path in which Q does not hold. So, if AFQ holds, then it also satisfy EFQ, right, because there is at least in all path it is happening, that means there is in one path it is also going to happen. So, EFQ also hold. but if EFQ holds, it does not mean AFQ holds. Okay. So, we will learn on more detail on this temporal logic, both CTL and LTL. Just today I just give you the glimpse of the temporal logic, right. So, let us now discuss what is the plan for this formal property verification part. So, I will start with talking about this correctness, consistency and completeness of the properties, because first task is to write the properties. So, I will take examples and I talk about that, and then I will introduce this LTL and CTL modeling. So, I will introduce the syntax, semantics of this LTL and CTL, and I will give some modeling example. I will take few examples and show you what will be the LTL modeling and CTL modeling, right. So, that you get comfortable on modeling something with LTL or CTL, right. Then as I mentioned, you need to know the algorithms, the magic happening behind these model checking tools, both for CTL and LTL. So, I will talk about the algorithm for LTL model checking and CTL model checking in detail in this course. And then one of the criticism of this formal property checking is the state explosion problem. As you mentioned, from the design I extract a transition system, and this transition system depends on the number of state variable you have in your design, right. State variable means your registers, memories. Now, you think about that, if a design has say 100 flip flops, in worst case your transition system may have 2 to the power 100 states, and that is impossible to model, right. So, many cases this model checker is not scalable if you try to explicitly try to model your the state transition system, where the state explosion problem happen, right. So, there are a lot of tricks has been developed which is called symbolic model checking, where we do not want to extract that exact model, explicit model, because that will create a state explosion problem, but I can model my that state transition system as a BDD. I have already talked about binary decision diagram. So, instead of modeling my state transition system as a FSM, I will model my this FSM this state transition system as a BDD. Then how this model checking algorithm can be done on BDD is the interesting thing, right. So, all the LTL and CTL property checking they will learn, we will see how we can do the same thing with BDD. Okay. Similarly, I can also model my transition system as a property. We have already seen that I can model a transition system as a SAT property, right. Similarly, I can take a instance or witness of my temporal property into the this propositional formulas, right. You remember in my SAT solving there is no until operator, there is no next operator and all, right. So, I cannot check their satisfiability using SAT solver, but I can actually create an interpretation of the temporal logic for say 1 cycle, 2 cycle, 4 cycle and 6 cycle, and that will be a propositional formula. I will remove all this until x, f operator, and what is their interpretation for 2 cycle, 3 cycle, 4 cycle, and that will be a Boolean propositional formula. So, then I can model my transition system as a propositional formula. I can witness, I can model my property as witness of a finite length as a formula, propositional formula. Then I can use the SAT solver to check the model checkers. So, I can utilize the SAT solver as model checker. Okay. So, we will talk about that. So, these are called symbolic model checking, and that actually make this model checker useful. Without this, there is no practical relevance of this model checker, because the state transition is too big. With invent of this BDD based model checker and SAT based model checker, there is a wide use of this model checking tool both in software industry as well as in hardware industries. Okay. And finally, I will also talk about the bounded model checking, which something very closely related to the SAT based model checkers. Okay. So, this will I will cover in kind of 4 weeks to 5 weeks. Okay. Thank you.